Somewhere inside a NOAA supercomputer facility right now, a specific decimal point is climbing. It is climbing slowly, quietly, and almost nobody in the mainstream media is talking about what that number actually means. If you look at the surface of the Pacific Ocean today, it projects an illusion of perfect safety. The Oceanic Niño Index, the primary vital sign of our global climate, is currently sitting at a marginal 0.16 degrees Celsius. To the general public, and even to a casual weather anchor, it is a number so close to zero that it registers as unremarkable, safe, neutral. But the world's most advanced predictive models do not believe the silence. The two most trusted, independently engineered forecasting systems on the planet, NOAA's CFSV2 and the North American Multi-Model Ensemble, are looking at that same quiet ocean and sounding a silent alarm. They are independently calculating a massive, violent spike in the Niño 3.4 region, with central estimates marching toward plus 2.1 to plus 2.2 degrees Celsius. This is not a standard weather forecast. When this index crosses 0.5 degrees, we have an El Niño. When it crosses 1.5, we have a strong, globally disruptive event. But when a forecast breaches the 0 degree threshold, you leave standard meteorology behind. You enter the rare and dangerous territory of the Super El Niño. The last times humanity crossed that line in 1982, 1997, and 2015. It redefined the meaning of planetary catastrophe. So, if the surface is neutral, why are the world's most powerful supercomputers bracing for a historic impact? Because the answer to what is coming doesn't lie on the water. It lies beneath it. To understand why the supercomputers are panicking while the horizon looks clear, you have to stop looking at the horizon. The greatest blind spot in how we track El Niño is our obsession with the surface. We wait for a red blob to appear on a satellite map off the coast of Peru, thinking that is when the event begins. But a Super El Niño does not begin with the warming of the surface. It begins with a massive, silent accumulation of thermal energy, hundreds of meters below it. Welcome to the Western Pacific Warm Pool. Think of this region as a planetary-scale thermal battery. For the past several years, during our extended La Niña phases, the Pacific trade winds have acted as a relentless engine, blowing steadily from east to west. These winds have physically pushed sun-warmed surface water across the ocean, piling it up against the western side of the basin. Because the water has nowhere else to go, it is forced downward. It deepens. It becomes insulated from the cooling effects of the atmosphere above it. The ocean does not lose this heat. It simply banks it in the dark, building pressure that the world above cannot see. But right now, in the spring of 2026, those trade winds are beginning to falter. When the winds weaken, the mechanism holding that water in place collapses. Gravity and ocean dynamics take over. That massive reservoir of trapped heat is now sliding eastward, moving entirely underwater in a phenomenon we call Kelvin waves. These are not the crashing waves you see on a beach. They are slow, enormous disturbances in the thermocline, the boundary layer between the warm upper ocean and the cold abyss. They carry enough thermal energy to reorganize the weather patterns of the entire planet. This brings us to a fundamental law of oceanic physics. El Niño is not the ocean gathering heat. El Niño is the ocean releasing the heat it has already stored. By the time you see the Niño 3.4 index cross that plus 0.5 degree threshold on your evening news, the real event is already halfway over. The ammunition is already in the chamber. The models aren't guessing what the surface will do. They are calculating the inevitable surfacing of energy that has been in motion for months. But even with a loaded battery and Kelvin waves in transit, we must ask, will the atmosphere actually pull the trigger? Because between a massive projection and a historic catastrophe, there lies one of the most inconvenient facts in all of atmospheric science, one that meteorologists call the barrier. If this were a simple story of cause and effect, The massive heat reservoir we just discussed would be a guarantee of catastrophe. But in the world of atmospheric science, there are no certainties, only probabilities. And right now, we are navigating the most treacherous window in the entire forecasting calendar. Meteorologists call it the spring predictability barrier. Every year, between February and May, the A conversation between the ocean and the atmosphere falls into a whisper. In the boreal spring, the temperature gradients across the equatorial Pacific reach their annual minimum, and the coupling that drives El Niño becomes fragile and easily disrupted by stochastic noise, random wind bursts that can either ignite a warming trend or snuff it out entirely. To trust a forecast made in April is to try and read a message written in pencil during a rainstorm. History is littered with the wreckage of confident spring forecasts. The year 2014 remains the ultimate cautionary tale for everyone in my field. Back then, the subsurface heat content was nearly identical to what we are seeing today. The battery was fully charged. The Kelvin waves were marching eastward. Every headline predicted a monster El Niño, but the atmosphere refused to pull the trigger. The trade winds did not stay weak. They recovered, pushing back against the ocean's heat, and the super event simply withered away. It taught us a vital lesson. The ocean can provide the energy, but the atmosphere must provide the cooperation. We also have to account for the personality of our machines. The NOAA CFSV2 model, the one showing those extreme plus 2.2 degree peaks, is known for its enthusiasm. It has a documented bias for overshooting El Niño peaks in long-range forecasts. If the CFSV2 says plus 2.2, an experienced analyst might mentally discount that to plus 1.8. This is why we look to the NMME, or the North American Multi-Model Ensemble. It isn't a single model. It's a jury of independent systems built on different physics and different assumptions. When the NMME agrees with the CFSV2, it means the signal isn't just a quirk of one computer's programming. It means the physical data is so loud that multiple independent minds are arriving at the same conclusion. So, as we move into the summer of 2026, we must track three possible realities. Scenario 1, the false start. The trade winds recover, the Kelvin waves dissipate, and the event remains a weak, manageable anomaly. Scenario 2, the strong standard. El Niño forms, reaches a peak of plus 1.5 to plus 1.8 degrees, and triggers significant weather disruptions, but stays within the bounds of what we've seen before. Scenario 3, the systemic lock-in. The atmosphere couples perfectly with the subsurface heat, breaching the plus 2 degree threshold. This is the Super El Niño kitchen barn, the one that reorganizes the global climate. If we want to understand the true magnitude of the risk we are discussing today, we have to look at a master key that was forged in the year 2018. It is a piece of scientific literature that almost no one outside of academic circles has ever read. Yet it holds the most important lesson for the world of 2026. The paper, authored by a researcher named Singh and a team of colleagues, set out to solve a geophysical murder mystery. They were looking back at a 3-year window between $1,876 and $1,878, a period known to historians as the Victorian Great Drought. It was a time when the rain simply stopped falling across multiple continents simultaneously. The resulting famines in India, China, Brazil, and Africa killed an estimated $50 million people. It was, quite literally, one of the deadliest climate events in recorded human history. For over a century, the scientific consensus was simple. A massive, record-breaking El Niño was to blame. But Singh and his team weren't satisfied with that answer. Using modern climate attribution methods and high-resolution data reconstructions, they asked a deeper question. Was the Pacific Ocean alone capable of causing a global collapse of this scale? Their conclusion was a turning point in atmospheric science. The Singh paper found that while a powerful El Niño was certainly present in $1,877, it was merely the headline. The actual mechanism that turned a strong weather event into a global catastrophe was something much rarer and far more dangerous. It was a perfect destructive synchronization of three separate ocean basins. They identified a Triple-Basin Alignment, consisting of three specific components. First, a very strong El Niño in the Pacific. Second, a massive positive phase of the Indian Ocean Dipole. And third, anomalously warm sea surface temperatures in the North Atlantic. When these three independent systems tuned themselves to the same frequency, they created what scientists call teleconnection stacking. Each ocean sent its own signal to the atmosphere, and instead of canceling each other out, they reinforced one another. The Pacific pulled moisture away from the tropics, the Indian Ocean blocked the monsoon flow into South Asia, and the North Atlantic distorted the jet streams, suppressing rainfall across the Americas and Africa. This is the three-ocean machine. It is a configuration where the climate ceases to be a collection of regional events and becomes a globally coherent drought signal. In $1,877, this machine worked with terrifying efficiency, ensuring that the rain failed everywhere, all at once. We are not looking at the Singh paper today because it is a prophecy of doom. History doesn't repeat itself in the exact same way. But $1,877 does not give us a script to copy. It gives us a mechanism to recognize. It tells us that we should stop obsessing over whether the Pacific El Niño is $1 plus $2 or $1 plus $2.2 event, and start looking at what the other two instruments in the climate orchestra are doing. Because for the first time in over a century, the data is suggesting that the rest of the orchestra is beginning to tune up. To understand why this triple-basin configuration is the ultimate stress test for our modern world, we have to look at the individual gears of this machine. We have to see how each daizung dongvai cha na, and how they are beginning to move in Haingin Lair, Haimui Sao. To understand why this triple-basin configuration is the ultimate stress test for our modern world, we have to look at the individual gears of this machine. We have to see how each daizung dongvai cha na, and how they are beginning to move in Haingin Lair, Haimui Sao. To understand why the 2026 forecast is causing such quiet alarm in research facilities, we have to stop treating these oceans as separate entities. They are not isolated basins of water. They are the synchronized gears of a single, planetary-scale machine. When Singh and his colleagues identified the Triple-Basin Alignment, they were describing a state where the individual signals of the climate system no longer cancel each other out. Instead, they stack. Let's disassemble this machine to see how the gears mesh. Gear 1. The Pacific Engine. A Super El Niño is not just a warming event, it is a violent reorganization of the Walker circulation. Under normal conditions, moist air rises over the western Pacific and falls over the east. In a Super El Niño, that loop is torn apart. The rising branch, the source of rain, shifts thousands of miles to the east. This leaves South Asia, Southeast Asia, and Australia trapped under the descending branch of the circulation. Descending air is dry air. It suppresses clouds. It bakes the soil. For a vast portion of the tropics, the Pacific Engine is already a formidable driver of drought. But on its own, the atmosphere often finds ways to compensate, unless the second gear locks into place. Gear 2. The Indian Ocean Multiplier. This is the Indian Ocean Dipole, or IOD. In 2026, we are watching a positive phase take shape. The western Indian Ocean becomes anomalously warm, while the eastern side cools. This creates a physical wall. The IOD governs the moisture conveyor belts that fuel the South Asian monsoon, the rainfall system that supports over 2 billion people. A positive IOD severs that moisture flow. If El Niño is already pulling the rain away to the east, The IOD ensures there is no backup supply from the west. When these two gears mesh, their drought signals don't just add up, they resonate, they amplify. They ensure the monsoon doesn't just underperform, it fails. Gear 3, the Atlantic Amplifier. This is the gear most mainstream forecasts ignore. For 3 consecutive years, the North Atlantic has held a record-breaking thermal surplus. By itself, a warm Atlantic doesn't necessarily mean a global disaster. But in this configuration, it acts as the third finger on the scale. It distorts the intertropical convergence zone and alters the subtropical jet streams. It modifies the large-scale pressure patterns that govern where moisture goes in Africa and the Americas. It acts as a stabilizer for the drought patterns already set by the Pacific and Indian Oceans, preventing the global circulation from correcting itself. This is the core concept of teleconnection stacking. Think of it like this. A single climate signal is a soloist. 2 signals are a duet. But 3 signals, all tuned to the same frequency of drought and disruption, are a planetary ensemble. They create a globally coherent state where the moisture-bearing systems that sustain human agriculture are simultaneously displaced, weakened, or suppressed across every inhabited continent. It is the physical signature of a system under total stress. The last time these 3 gears locked together in this exact pattern, the world did not just experience a dry summer. It experienced a reorganization of the human map. To understand what happens when this machine reaches full power, we have to look at the year the rain simply stopped. When we speak of the years 1876 to 1878, we are not describing a bad season or a regional dry spell. We are looking at a desiccated ghost that haunts the very foundations of modern meteorology. In those 3 years, the 3-ocean machine reached its full, terrifying resonance, and the result was a globally synchronized atmospheric collapse. The hallmark of this catastrophe was not just the intensity of the drought, but its simultaneity. In the modern world, we rely on the fact that if a harvest fails in one hemisphere, the other can compensate. Our global food security is built on the statistical improbability of everyone failing at once. But 1,877 proved that under the right oceanic configuration, that improbability becomes a certainty. It began in India. The South Asian monsoon is the most critical heartbeat of the planet, delivering 80% of the annual rainfall to nearly a quarter of the human population in just 4 months. In 1876, and again in 1877, that heartbeat stopped. The combination of a Super El Niño pulling the air away and a positive Indian Ocean Dipole blocking the moisture flow meant the rains didn't just underperform, they vanished. In some regions, rainfall was less than 25% of normal. Agricultural systems that had sustained millions for millennia were pulverized in a single season. Simultaneously, thousands of miles to the northeast, the same machine was crushing China. The provinces of Shanxi, Henan, and Shandong, the agricultural heartland of the Qing dynasty, experienced a drought so severe that tree ring records suggest it was the worst in at least 3 centuries. The death toll in China alone is estimated between 9 and 13 million people, but the machine wasn't finished. In Brazil's Nordeste region, the Grande Seca, the Great Drought, set in. The North Atlantic heat anomaly, acting as the 3rd gear, pushed the intertropical convergence zone northward, leaving the Brazilian interior to bake in a multi-year heat wave that killed 500,000 people and triggered mass migrations that reshaped the human geography of South America forever. From the Horn of Africa to the plains of Australia, the story was the same. The 3-ocean machine had imposed a common, devastating drought signal on the entire planet. This is the true power of teleconnection stacking. It forces the atmosphere into a state where it simply cannot fix itself. Usually, if one basin is warm, another is cool, providing a balance. But in 1877, every major moisture-producing mechanism was suppressed. The air over the world's breadbaskets was forced to sink, and sinking air cannot produce rain. 50 million people died, not because of a single storm, but because of a synchronized silence of the clouds. But to understand the full weight of this for our world in 2026, we have to ask a darker question. Why was the death toll so high? Was it purely the weather? Because the uncomfortable truth is that the climate only provided the pressure. It was the human systems of the time, the markets, the policies, and the institutions that turned a climate anomaly into a mass grave. And as we look at 2026, we have to ask, have our systems really become more resilient? Or have we just built a more complex way to fail? It is a comfortable fiction to blame the sky alone for the deaths of 50 million people. It allows us to view the Victorian Great Drought as a tragic accident of nature, an act of a chaotic God that we, with our modern technology, have since outgrown. But the data tells a far more unsettling story. The three-ocean machine provided the physical pressure. It created the heat and suppressed the clouds. But climate only creates the conditions for failure. It is the human system that determines the lethality. In 1877, the death toll reached apocalyptic proportions because the global political and economic systems of the time were not designed to absorb a shock. They were designed to pass it through to the most vulnerable. Take the case of British India. This is perhaps the most documented and devastating example of what happens when a climate anomaly meets an ideological dogma. The British colonial administration, governed by a rigid adherence to laissez-faire economics, refused to intervene in the food markets. Their logic was cold and mathematically precise. The market would solve the scarcity. But the market did not favor the starving subsistence farmer in the Deccan Plateau. It favored the high-income buyer in London. Throughout the peak of the drought in 1877, India continued to export record amounts of wheat and rice. The food was physically present. It was sitting in granaries and moving on ships. But the market price, driven by global demand, was higher than the purchasing power of the dying. The newly built railroad network, often praised as a tool of modernization, functioned during the famine as a giant vacuum, sucking grain out of the drought-stricken interior and toward the coastal ports for export. In Qing China, the failure was different but equally systemic. A once sophisticated empire, which for centuries had maintained the gold standard of national granaries and famine relief, had been hollowed out by decades of internal rebellion and external colonial pressure. When the three-ocean machine shut off the rains in the northern provinces, the state apparatus simply lacked the administrative bandwidth to respond. The infrastructure was broken. The treasury was empty. The climate applied a load to a structure that was already riddled with cracks. It wasn't just the drought that killed 13 million people in China. It was the collapse of a social contract that had previously protected them from the sky. This is the central takeaway that most mainstream climate discussions miss. A natural disaster is never purely natural. It is the point where an atmospheric anomaly meets a human fragility. In the 1870s, that fragility was colonial extraction and market orthodoxy. The system was optimized for the flow of capital, not the preservation of life. When the Triple-Basin Alignment struck, the system did exactly what it was designed to do. It protected the center and sacrificed the periphery. Why does this matter for us in 2026? Because every era builds its own unique architecture of fragility. We often look at the 1870s and think we are safe because we no longer live in a world of steamships and colonial grain monopolies. But as we watch the Pacific, the Indian, and the Atlantic Oceans align once again, we have to ask, what is the fragility of our own time? What happens when the three-ocean machine strikes a world that is not Victorian, but one that is optimized for something else entirely? It is at this point that we must pause. When we discuss the deaths of 50 million people and the synchronization of three ocean basins, the human mind naturally gravitates toward a singular, terrifying conclusion: that history is a circle, and we are simply waiting for the scythe to swing again. But I am here to tell you that 2026 is not 1877. To believe that we are destined for a direct repeat of the Victorian catastrophe is to ignore a century of the most profound technological and humanitarian advancement in human history. In the 1870s, the world was flying blind. They didn't even have a name for El Niño. There were no satellites to watch the clouds, no sensors to feel the pulse of the deep ocean, and no global network to whisper a warning before the rain stopped. Today, we live in a world of total visibility. We are no longer guessing. We have the Argo float network, nearly 4,000 autonomous robots patrolling the global ocean, diving 2 kilometers deep to measure temperature and salinity every 10 days. We have the TOWEL, Triton mooring array, a permanent line of sentinels across the equator that feels the Kelvin waves the moment they begin their eastward march. In 1877, the drought was a surprise. In 2026, the three-ocean machine is a detectable, measurable event. We have the gift of lead time. Furthermore, the moral and political architecture of our world has fundamentally shifted. In 1877, the prevailing ideology was one of colonial extraction, and Malthusian neglect the idea that famine was a natural check on population. Today, we have the World Food Program, the FAO, and a global network of NGOs. We have an international social contract that, however imperfect, recognizes mass starvation as a failure of humanity, not a law of nature. Our agriculture is different too. We have drought-resistant crop varieties, sophisticated irrigation systems, and a logistical capacity to move millions of tons of food across the planet in weeks, not months. Current data does not predict a global famine. It does not predict the collapse of civilization. The most important thing to maintain scientific credibility is to acknowledge that we are now stronger, better prepared, and more connected than ever before. But, and this is the but that keeps climate analysts awake at night, saying that 2026 is not 1,877 is not the same as saying we are safe. It simply means our vulnerabilities have changed. We have traded the brittle fragility of the Victorian era for the complex fragility of the modern world. We no longer fear the failure of a wooden plow. We fear the failure of a global, just-in-time supply chain. We no longer fear the silence of a colonial governor. We fear the volatility of a global commodity market. Because while we have built better tools, we have also built a different world. And the three-ocean machine of 2026 is not operating on the same planet it did a century ago. The stage has been rebuilt, the fuel has been changed, and the baseline has shifted. We have reached a physical threshold where historical comparisons begin to fray. To understand why the 2026 three-ocean machine is more dangerous than its 1,877 predecessor, we must accept a fundamental law of thermodynamics. Every El Niño from this point forward is occurring in a world that is fundamentally more energetic than any point in human record. In the late 19th century, the global mean surface temperature was the baseline. Today, we are operating in a climate that has warmed by approximately $1.2 to $1.5 degrees Celsius. That might sound like a small shift, but in the language of physics, it represents a total reorganization of the planet's energy balance. The core of this reorganization is the Clausius-Clapeyron relation. This physical principle dictates that for every 1 degree of warming, the atmosphere's capacity to hold moisture increases by about $7 per cent dollar. This is the fuel of the modern anomaly. A warmer atmosphere is a thirstier atmosphere. When the three-ocean machine shifts the rainfall patterns, it doesn't just leave a region dry. It actively strips moisture from the landscape with a speed and intensity our ancestors never witnessed. This creates a phenomenon known as flash droughts. Because the air is hotter, the evaporative demand is higher. The atmosphere essentially reaches down and sucks the water out of the soil, the reservoirs, and the plants themselves in a matter of weeks rather than months. Anthropogenic warming does not necessarily create the Triple-Basin Alignment, but it loads the dice. It ensures that when the Indian Ocean Dipole blocks the monsoon, or when El Niño suppresses the clouds, the resulting heat is not just seasonal, it is record-breaking. The baseline has shifted. We are no longer watching a natural cycle play out on a stable stage. We are watching a natural cycle play out on a stage that has been saturated with heat. This intensified cycle has two faces. In the regions where the moisture is being stripped, the droughts are deeper and the wildfire risks are exponential. But that moisture has to go somewhere. In the regions where the rain does fall, like the US South or coastal East Africa, it doesn't just rain, it deluges. The same $7 dollar increase in moisture capacity means that when the clouds finally break, they release atmospheric rivers that can wash away a season's worth of topsoil in a single afternoon. This is the new baseline. Climate change does not write the script of El Niño. It simply changes the physics of the theater. It ensures that the three-ocean machine hits harder, moves faster, and leaves less room for recovery. And when this intensified physical pressure slams into a modern, globalized society, it doesn't hit a world of local farmers and steamships. It hits a world that is interconnected by a single, massive, and terrifyingly efficient engine. To understand the 2026 risk, we must look at the second machine, not the one in the oceans, but the one we built ourselves. We have to look at the global food machine. If the three-ocean machine is the physical hammer, then the global food machine is the glass structure it is about to strike. To understand the risk of 2026, we have to stop thinking about farms as isolated patches of dirt. In the Victorian era, if a harvest failed in the Deccan Plateau, the catastrophe was largely contained within the borders of the empire. Today, there is no such thing as a local harvest. We have spent the last 50 years building the most efficient, integrated, and high-speed food delivery system in human history. It is a logistical masterpiece. But it was designed for a world of climate stability that no longer exists. The core philosophy of the modern world is efficiency. We have optimized every link in the chain to eliminate waste. In business terms, waste is a buffer. Waste is a warehouse full of grain sitting idle, just in case. In our pursuit of profit and speed, we have moved to a just-in-time supply chain. We no longer store years of food. We store weeks of it. The global food supply is currently a continuous flowing river. As long as the river keeps moving, the world eats. But this efficiency has come at a staggering cost. We have removed the shock absorbers. This is the efficiency paradox. The more integrated a system becomes, the faster a local shock turns into a systemic collapse. When the three-ocean machine strikes in 2026, it isn't hitting a collection of independent silos. It is hitting a web where India provides 40% of the world's rice exports. Brazil dominates the global soy and corn markets. Southeast Asia drives the world's palm oil and coffee supply. In a normal year, if one of these regions falters, the machine reroutes. We buy more from the US. We shift to Australian wheat. But the Triple-Basin Alignment is the ultimate nightmare for this system because it is a synchronized shock. If the Indian Ocean Dipole parches the Punjab at the same time El Niño bakes the Brazilian interior and shifts the rains away from Indonesia, the machine has nowhere to turn. It cannot reroute because the alternative sources are also under pressure. When supply drops simultaneously across multiple breadbaskets, we don't just see a shortage of food, we see a volatility spike. In the digital age, commodity traders react in milliseconds. Prices don't rise, they explode. And as we saw in 2008 and 2022, when food prices spike, the machine doesn't just stutter. It triggers a chain reaction of export bans, civil unrest, and political destabilization. The modern world isn't vulnerable because we lack food. We produce more calories than ever before. We are vulnerable because we have built a system that requires perfect synchronization to function, and we are about to hand the controls of that system over to three oceans that are out of sync. To see where the first cracks will appear, we have to look at the nations sitting on the front lines of this alignment. The three-ocean machine does not distribute its pressure evenly. It is a planetary-scale redistribution of life-giving water. And in 2026, the first places to feel the gears grind are those where the margin for error is thinnest. We begin with the heartbeat of the world, South Asia. For over 2 billion people, the South Asian monsoon is not just a seasonal forecast, it is the currency of survival. As the Triple-Basin Alignment locks in, this heartbeat begins to falter. A Super El Niño in the Pacific pulls the rising air, the rainmaker, away to the east. Simultaneously, the positive Indian Ocean Dipole blocks the moisture conveyor belts from the west. This double whammy doesn't just mean less rain. It means a fundamental displacement of the sowing schedules. If the rains are delayed by even 3 weeks, the heat of the pre-monsoon season bakes the soil into a brick-like state, ensuring that when the rain finally arrives, it runs off rather than soaking in. As the regional harvest shrinks, we see the first crack in the global food machine. India, the world's largest rice exporter, facing an internal crisis that forces an external ban. When 40% of the world's rice market vanishes to protect domestic stability, the shockwave travels at the speed of a digital trade. Moving to sub-Saharan Africa and the Horn, the crisis takes a different form. These regions are often the canaries in the coal mine for the teleconnection signals of the Indian Ocean. For communities already pushed to the brink by consecutive failed seasons, a synchronized climate shock is not just an agricultural problem, it is a solvency problem. The danger here is the price-out phenomenon. Even if local crops manage to survive, the global spike in grain prices caused by failures in Asia and Brazil means that basic sustenance becomes a luxury. When a household spends 60% of its income on food, a 20% price hike is not an inconvenience, it is a catastrophe. In northeast Brazil, the historical ghosts of the Grande Seca begin to stir. The third gear, the North Atlantic heat, acts as a thermal lid, pushing the intertropical convergence zone away from the Brazilian interior. This region is uniquely sensitive to the Triple-Basin Alignment. When the Atlantic is too warm and the Pacific is in a Super El Niño, the Sertão doesn't just experience a drought, it experiences a multi-year desiccating event that pressures the entire national economy of South America's largest power. Meanwhile, across Southeast Asia and Australia, the big dry sets in. The cooling of the eastern Indian Ocean and the warming of the central Pacific create a massive zone of sinking dry air. Reservoirs in Vietnam and Thailand drop to critical levels, and the smoke season in Indonesia threatens to become a permanent fixture of the 2026 calendar. But we must maintain scientific balance. El Niño is a zero-sum game. It does not destroy water, it redistributes it. While the three-ocean machine parches the breadbaskets, it sends a deluge elsewhere. Coastal Peru and Ecuador may face catastrophic flooding as the warm water piles up against their shores. Parts of East Africa and the southern United States may see unprecedented atmospheric rivers. The risk here isn't thirst. It's the total washout of infrastructure and the spread of waterborne diseases. The machine is not a local story. It is a story of a planet being forced into a new extreme equilibrium. And as we sit here in the spring of 2026, we don't have to wait for the harvest to fail to know it's coming, because the atmosphere is already starting to send its first echoes. The atmosphere is not a patient system. It does not politely wait for a Pacific temperature index to reach its absolute peak before it begins to reorganize the global circulation. When the Central Pacific starts to warm, the teleconnections, the invisible atmospheric wires that link our weather systems, begin to hum almost immediately. Even now, as we navigate through April 2026, the first atmospheric echoes are already ringing. To a casual observer, these might look like isolated weather events, but for those of us tracking the three-ocean machine, they are the physical fingerprints of a system beginning to lock into place. We are moving out of the realm of supercomputer projections and into the realm of real-world observation. Let us look at the Western Pacific. Usually, at this time of year, we expect a specific pattern of tropical activity, but the early data shows a significant eastward shift in the formation zones of tropical cyclones. The storms are tracking toward the Central Pacific far earlier and more aggressively than they should. This is a classic early onset signal of an atmospheric reorganization, a shift in the Hadley cell that occurs only when the ocean is exerting a massive amount of upward pressure on the sky. The atmosphere is already shifting its weight, preparing for a Super El Niño before the Niño 3.4 index has even reached its peak. Now, look at the Indian Ocean. The early wind data across the equator is showing an unusual reversal. The trade winds that typically feed moisture into the Indian subcontinent are stalling. We are seeing the signature of a positive Indian Ocean Dipole manifesting in the atmosphere before the water itself has reached its full thermal gradient. The monsoon is already vibe-checking the system, and the response is one of hesitation. For the billions in South Asia, these early stalls are the first whispers of a late and weakened rainy season. Simultaneously, the North Atlantic is acting as a thermal stabilizer for these disruptions. The persistent, record-breaking marine heat waves we've tracked for 3 years are preventing the normal seasonal cooling of the subtropical high-pressure systems. This is the third gear in action. It is distorting the Intertropical Convergence Zone, ITCZ, effectively pulling the moisture belts away from the Horn of Africa and northeast Brazil months before the summer season has even begun. A single anomaly can be dismissed as atmospheric noise. A record-breaking heat wave in the Atlantic or a late monsoon in India could, in isolation, be a quirk of the weather. But when multiple distinct signals across 3 separate ocean basins all lean in the exact same direction, the story becomes a coherent narrative. What we are witnessing in April 2026 is the atmosphere responding to the ammunition that has been stored in the ocean for months. The signals are loud, they are synchronized, and they are following the blueprint of the Victorian Great Drought. But as these echoes grow louder, we must remain rigorously honest with the science. Because as compelling as these signals are, there is still a window for the system to change its mind. If we want to understand the 2026 risk, we must look at the off-ramps, the reasons why this entire nightmare could still fail to materialize. If we were to treat these supercomputer models as a guaranteed map of the future, we would be doing bad science. To maintain the calm authority we've established, we must stop right here and look at the off-ramps. We must acknowledge the reasons why this entire terrifying narrative could still fail to materialize. The atmosphere is a chaotic system, and history is littered with the wreckage of confident spring forecasts that led to nothing. If the 3-ocean machine fails to lock in, it will be because of 3 specific scientific hurdles that we must monitor with equal intensity. First, there is the spring predictability barrier. We are currently in the most volatile window of the year. Between February and May, the physical conversation between the ocean and the atmosphere is at its weakest. It is like trying to predict the winner of a marathon while the runners are still tying their shoes. The most common way this super event fails is if the Pacific trade winds stage a surprise recovery. If a series of strong easterly wind bursts occurs in the next 60 days, they will act like a giant brake. They can physically push back against the Kelvin waves, forcing that stored subsurface heat to dissipate before it ever reaches the surface. This is what happened in 2014. The ammunition was there, but the trigger was never pulled. Second, we have to account for the model bias. The NOAA CFSV-2, which has been our primary alarm bell, is an optimist for heat. In our community, it is well known that the CFSV-2 tends to run hot. It has a documented tendency to over-forecast the speed and intensity of El Niño development during the spring months. If the other ensemble members, like those from Europe or Japan, don't begin to converge on the same extreme numbers, we must consider the possibility that the CFSV2 is simply shouting at shadows. Third, and perhaps most importantly, is the issue of atmospheric coupling. An El Niño is not just a warm ocean. It is a warm ocean that successfully convinces the atmosphere to change its behavior. If the Pacific warms, but the Indian Ocean Dipole remains neutral, or if the Atlantic heat remains isolated, the Triple-Basin Alignment never forms. The signals remain regional and manageable. Without that atmospheric lock-in, the three-ocean machine remains just a set of disconnected parts. Therefore, we are not looking at a single destiny, but at three distinct timelines. Timeline 1. The dud. The winds recover, the heat dissipates, and the year remains climatologically unremarkable. Timeline 2. The standard strong. A significant El Niño forms, causing typical disruptions, but stops short of the super threshold. Timeline 3. The systemic risk. The ocean and atmosphere couple perfectly. The Indian and Atlantic basins synchronize, and we enter the 1877 analog. The question is no longer, is this definitely happening? The question is, what must we monitor to know which timeline we are entering? To move from speculation to preparation, we have to watch the 6 signals. To treat supercomputer models as a guaranteed map of the future is to engage in bad science. If we are to maintain the calm authority we've established, we must stop right here and look at the off-ramps. We must acknowledge the reasons why this entire terrifying narrative could still fail to materialize. The atmosphere is a chaotic system, and history is littered with the wreckage of confident spring forecasts that led to nothing. If the three-ocean machine fails to lock in, it will be because of 3 specific scientific hurdles that we must monitor with equal intensity. First, there is the spring predictability barrier. We are currently in the most volatile window of the year. Between February and May, the physical conversation between the ocean and the atmosphere is at its weakest. It is like trying to predict the winner of a marathon while the runners are still tying their shoes. The most common way this super event fails is if the Pacific trade winds stage a surprise recovery. This is known as stochastic forcing, random wind bursts that act like a giant brake. If a series of strong easterly wind surges occurs in the next 60 days, they will physically push back against the Kelvin waves, forcing that stored subsurface heat to stay deep and dissipate before it ever reaches the surface. This is exactly what happened in 2014. The ammunition was there, but the trigger was never pulled, and the monster El Niño simply withered into a non-event. Second, we have to account for the model bias. The NOAA CFSV2, which has been our primary alarm bell, is an optimist for heat. In the climate community, it is well known that the CFSV2 has a documented tendency to over-forecast the speed and intensity of El Niño development during the spring months. It tends to run hot. If the more conservative European models like the ECMWF don't begin to converge on these extreme $+2.2 circ text C dollar numbers within the next few weeks, we must consider the possibility that our most aggressive projections are simply shouting at shadows. Third, and perhaps most importantly, is the issue of atmospheric coupling. An El Niño is not just a warm ocean. It is a warm ocean that successfully convinces the atmosphere to change its behavior, a process called the Bjerknes feedback loop. If the Pacific warms, but the Indian Ocean Dipole remains neutral, or if the Atlantic heat remains isolated and fails to distort the jet stream, the Triple-Basin Alignment never forms. The signals remain regional and manageable. Without that atmospheric handshake, the three-ocean machine remains just a set of disconnected, harmless parts. Therefore, we are not looking at a single destiny, but at 3 distinct timelines. Timeline 1. The dud. The winds recover, the heat dissipates, and the year remains climatologically unremarkable. Timeline 2. The standard strong. A significant El Niño forms, causing typical disruptions, but stops short of the historical super threshold. Timeline 3. The systemic risk. The ocean and atmosphere couple perfectly, the Indian and Atlantic basins synchronize, and we enter the 1877 analog. The question is no longer, is this definitely happening? The question is, what must we monitor to know which timeline we are entering? To move from speculation to preparation, we have to watch the 6 signals. As of today, the 24th of April, 2026, we are standing at the edge of the spring predictability barrier. To move from the realm of what if to the realm of what is, we need more than just a single alarm bell. We need a checklist of physical evidence. If we are to avoid the fate of the Victorian era, we must monitor the 6 signals. These are the indicators that will tell us if the three-ocean machine is merely warming up or if it has successfully locked into a gear that will reorganize our world. Signal 1. The Niño 3.4 threshold. This is the gold standard of ENSO monitoring, measuring the surface temperature in the Central Pacific from $170 circ text W dollar to $120 circ text W dollar. Watch this number with precision. We are looking for more than just a breach of the dollar plus 0.5 circ text C dollar El Niño baseline. We are watching for the velocity. If this index breaches dollar plus 1.5 circ text C dollar by midsummer and continues to march toward the dollar plus 2 circ text C dollar mark, the Super El Niño is no longer a projection, it is a physical fact. Signal 2. The ensemble spread. In forecasting, we don't look for a single line, we look for a tightness in the data. If the CFSV2 and the NMME continue to converge on the same extreme peaks, the ensemble spread narrows. A narrow spread means the machines are in agreement. If the models stay locked together through the end of May, the statistical probability of a dud drops to nearly 0. Signal 3. Westerly wind bursts, WWBs. This is the trigger. We are looking for a massive, sustained collapse of the trade winds across the Central Pacific. Specifically, we are watching for westerly wind bursts episodes where the winds actually reverse direction. These bursts are the physical push that sends the subsurface heat to the surface. Without these, the Kelvin waves stay deep. With them, the ammunition is fired. Signal 4. The surface eruption. Watch the Tahoe, Triton moorings, off the coast of Peru and Ecuador. We are looking for the exact moment the subsurface battery we discussed in Chapter 2 hits the coast. When those deep Kelvin waves finally erupt onto the surface, we will see a sudden violent rise in local sea surface temperatures. Dollar, delta T, dollar. This is the point of no return for the Pacific engine. Signal 5. The positive IOD transition. This is Gear 2. We must monitor the Dipole Mode Index, DMI, in the Indian Ocean. If the western basin near Africa warms significantly while the eastern basin near Indonesia cools, the IOD has turned positive. If this happens in synchronization with the Pacific warming, the South Asian monsoon is in immediate, systemic danger. Signal 6. Atlantic thermal stability. Finally, we watch the North Atlantic. Is the record-breaking heat of the last 3 years finally dissipating, or is it holding its ground? If the Atlantic remains at these extreme levels into the peak of the hurricane season, it will continue to act as the third gear, stabilizing the global drought signal and ensuring the three-ocean machine remains at full power. If all 6 of these signals turn amber by June, we are no longer discussing a weather forecast. We are discussing a planetary stress test. But there is one final piece to this puzzle. Because as the data grows louder, we must realize that the most dangerous part of this anomaly isn't the data itself, it's us. We have reached the end of our current data stream, but we are only at the beginning of the event. As of the 24th of April, 2026, the three-ocean machine is no longer a theoretical ghost from 1877. It is a physical reality taking shape in our telemetry. We do not share this analysis to invoke panic. Panic is a biological short circuit. It is the enemy of preparation and the end of rational thought. If your reaction to this data is to feel a sense of impending doom, you are missing the point. We track these anomalies precisely because we refuse to be victims of them. Information is the only thing that turns a disaster into a manageable challenge. The unsettling aspect of the 2026 anomaly is not that we know exactly what will happen. It is that the signals are loud enough to demand immediate monitoring, yet just subtle enough for the mainstream world to ignore them until the impact is already embedded in the supply chains. The ocean doesn't have a PR team, and the atmosphere isn't interested in your social media feed. It doesn't need to scream to be dangerous. It doesn't need a 100-foot tidal wave or a Hollywood-style apocalypse. It only needs to shift by a few tenths of a degree, perhaps a thermal delta of just 0.5 degrees Celsius, in the exact right place, at the exact right time, in perfect synchronization with two other oceans. When that happens, the question ceases to be about the weather. It becomes a question about the systems we have built to sustain ourselves. Is our highly optimized, just-in-time global machine capable of absorbing a simultaneous, multi-basin shock? Or have we traded our resilience for a fragile efficiency that cannot handle a three-ocean pulse? In 1877, the world died in the dark. They had no satellites, no models, and no choice but to wait for the rain that never came. In 2026, we have the gift of lead time. We can see the Kelvin waves. We can track the IOD. We can anticipate the price spikes in rice, wheat, and energy months before they hit the supermarket shelves. This is not an end-of-the-world story. It is a story about the end of a specific type of stability. It is a call to move from the pre-event mindset to the active monitoring phase. It is about auditing your own household's resilience, your local community's resources, and your own understanding of the global gears. The ocean has made its move. The atmosphere is currently formulating its answer. As the data evolves through May and June, we will be here to translate it. We will be watching the Niño 3.4 index, the westerly wind bursts, and the North Atlantic persistence. We will be looking for the handshake between the sky and the sea. Leave your location in the comments to join our global observation network. Tell us what you are seeing on the ground, whether it is an unseasonable heat wave in Brazil or a delayed monsoon in India. Local observation is the final check on global models. Stay vigilant, stay grounded in the data, and above all, stay prepared. The machine is moving. Are you?